In this lesson, we're going to build our simulated network environment, so let's get started. I will click on the Network Devices button, choose Routers, and I will use 5 of these 4321 routers. Now you can use whichever routers you want, and as many or as few as you want, but I will use 5 so that we have a nice variety of routes for our protocol to choose from. And I also want to have one isolated network over here so that we can learn the contrasts between the different routing protocols. Now let's connect our devices. And to add a little bit more variety to our lab, let's use a combination of crossover cables and serial cables. But before we can do that, we have to turn off the power on each of these 4 routers so we can install a new network interface card that supports serial cable connections. So let's do that. So we simply turn off the power, install the NIC, and turn the power back on. And we need to do this for each of these 4 routers. Now we are ready to connect our devices. And that looks good. Now the next thing I'm going to do is relabel each of these routers. That way it will be a little bit easier for us to know which router we're talking about when we're in the work area. So I'll do that right now. Now let's label each of our networks, and to do this I will use Class A addresses just to keep it simple. And now all we have to do is statically assign IP addresses to each of our interfaces and no shut them, and also configure host names for each of our routers that correspond with their labels. That way when we are logged into a router, we will know which one we're on. And I will start with router 1. And if you get this message asking you if you want to use the setup wizard, just say no, because we want to do all the configurations ourselves. So let's log in, go to global configuration mode, and begin our configurations. And this last command is to save the configuration. So I suggest you use the WR command whenever possible. That way you will be saving your configurations. And that all looks good. And we can further verify our configurations by simply mousing over each device. And you may have noticed that when I was assigning IP addresses to the interfaces of each router, that I was also using the same number as the host name. So router 1 has addresses ending with .1, router 2 has addresses ending with .2, and so on. Now we're ready to configure our protocol, and we'll do that in Lesson 2. Welcome to Lesson 2. Before we begin configuring our protocol, let's verify that we can ping between interfaces on our LANs, and more importantly, that we cannot ping beyond our LANs. And let's also verify that there are no routing protocols running on any of our networks. And to do that, I'm going to use router 2. So let's log in, and let's start with a show IP protocol command, and we can see that nothing is reported because there are no routing protocols on router 2. Let's do a show IP route command and see what networks that router 2 knows about. And router 2 only knows about the networks that it is directly connected to. It knows about the 7000 network, 9000 network, and the 10,000 network. And we can even do a show CDP neighbors command. CDP stands for Cisco Discovery Protocol. And we can see that router 2 has 3 neighbors. They are Cisco devices, of course. And we can see that their capability is R for router. So these are the 3 routers, R4, R3, and R1. Now let's try to ping these routers. So let's start with router 1. And yes, we can ping router 1, no problem. Let's ping router 3. Yes, we can. And let's try pinging router 4. And yes, we can. Now let's try pinging, how about the 11,000 network? And right away we can see there is some delay, and we can see that our pings are timing out. And this is because router 2 does not know how to get to the 11,000 network. And we can verify this even further if we try to ping the router on the 12,000 network, which is router 5. And we should get a similar result. Our pings will all time out, and it looks like that is happening. So we do have connectivity on the networks that router 2 is directly connected to, but router 2 does not know how to get to the 8,000 network or the 11,000 network or the 12,000 network. And so that is as it should be. And of course, if you would like to, go ahead and test all the routers in our work area. But I am confident that none of them can ping or communicate outside of their immediate LAN. So we can now proceed with configuring our protocol. So let's begin. I'm going to start by logging into router 1 and go immediately to global configuration mode. And here all we have to type in is router OSPF followed by a question mark. And here we are prompted to choose a process ID number. And we can choose a number, any number within this range. Right here I want to point out that unlike EIGRP, which uses autonomous system numbers, Process IDs in OSPF do not have to match on each router. So unlike EIGRP, if we chose an AS number of 1, then all the routers in that environment would also have to have an AS number of 1. But in OSPF, the process ID on each router can be different if we want it to be different. So I'm going to choose for this router, router OSPF process ID 1, just because I would like it to match the host name of this device. But you can name your process ID anything you like within this range. Now when I enter a question mark, we get a new list of options here. And OSPF is one of those protocols that requires that you configure it in a particular order. So after we choose our process ID, if we are going to manually assign a router ID, we have to do that now. And I'm going to do that for this router. And the thing about OSPF is that the router ID must be unique on each router, just like it would be in EIGRP or other routing protocols for that matter. And this is important because router IDs are one of the factors used between routers to form neighbor relationships within the OSPF environment. Now, if we do not assign a router ID to a router, it will choose its own ID, and how it does that is by preference. Now, if we assign an ID, that takes preference over everything, and that is the ID that the router will use. But if we do not assign an ID, then the router will choose an ID for itself. It will choose the highest loopback address it has, but if it doesn't have a loopback address assigned to it, then it will choose the highest IPv4 address it has on one of its interfaces. But I'm going to assign a router ID to this router and to most of the other routers except for router 2. That way we can see how router 2 chooses its own router ID. So here I'm going to enter in the question mark to see our instructions, and we can see that when we enter a router ID, it has to be in the same format as an IPv4 address, and we can see that because it must be a decimal number. So that's what I'm going to enter, and again I will keep it the same as the host name, so I will simply make it 1.1.1.1. And now we can move on to choosing another option, and we will use the network command option. So I will type in network, and here I will enter in the networks that this router will be routing for in OSPF. So we know that this router is directly connected to the 7000 and 8000 networks. So I will begin with the 7000 network. I will enter a question mark to see if there are any instructions, and there are. And here we see something a little bit unusual. We see a decimal number that we have to enter, but it has to be entered as wildcard bits. Now, what a wildcard bit is it means that we are going to be entering an inverse mask for this network. So instead of having 255.0.0.0, we're going to enter in 0.255.255.255. And the reason we're going to do this is because a wildcard mask or wildcard bits or inverse mask, whichever you want to call it, does not actually mask the network, not in the way that we typically think of. In other words, it tells OSPF what to do instead of telling the devices on this network what the boundaries are of the network. So what it's going to do when I type in 0.255.255.255, what's happening is I'm telling OSPF that any packet that is destined for the 7000 network must have a 7 in the first octet And then I don't care what's in these other 3 octets. So instead of telling the devices on the 7000 network what the boundaries are of this network, we're actually telling OSPF what to do instead of telling devices on the network what to do. Now when I enter a question mark here, we get some new instructions, and we have to choose an area ID. Now this is one of the requirements in OSPF, and that is the first area created in an OSPF environment must be the backbone, and that is area 0. So we always start counting from 0 when we create areas in OSPF. So once we've created this backbone area, if we wanted to create a multi-area OSPF environment, then we can make the next area would be area 1 if we wanted. So I will use the up arrow key just to save some time and do the same thing for the 8000 network. And that's all there is to it. And now I will save the configuration and repeat a similar set of commands on each of the other routers, again not choosing a router ID for router 2 so we can watch and see which router ID it chooses for itself. And we can see that router 2 has already formed a relationship with router 1. And that all looks good. Now in the next lesson, we're going to verify our configurations, and we're also going to learn some new show commands that will help us to manage and troubleshoot OSPF. Let's verify our OSPF configurations. I'm going to start with router 1. And the first thing I'm going to do is issue a basic show run command. And this gives us a lot of good basic information. And what I want to look for here is verification of which routing protocol we are running on this device. And we can see it is OSPF. That is correct. We see process ID 1. We can see the router ID that we manually assigned to this device of 1.1.1.1. And we can see the two networks, 7000 and 8000, that this router is sharing with the other routers via OSPF. Now let's issue a show IP route command. This will return the basic vanilla routing table, and right away we can see a lot of new information. We can see 4 new routes have been added to this routing table, and we can see by this letter O that they were learned via OSPF. So that all looks good. We can see the default AD or administrative distance of 110, which is the AD for OSPF. And after the / in each of these brackets, we can see the cost that was calculated by OSPF for each of these routes. Further, we can see which router R1 is using to reach those other networks, and it is router 3. Now another thing that you might have noticed here is the huge disparity between the cost to route to the 11,000 network versus the other 3 networks. Well, the reason for that is that in OSPF you must count the cost of the destination network in the total cost. And in OSPF, a gigabit link has a cost of 1 by default, and a serial link has a cost of 64 by default. So when we add those two together, 1 plus 64, we get the total routing cost, according to OSPF, of 65. So that all looks good. Now let's log into router 3. And here I'm going to issue 2 commands. First command is show CDP neighbors. CDP stands for Cisco Discovery Protocol, and it was written so that Cisco devices could detect other Cisco devices on a network, but it will work with some other manufacturer devices. And I'm going to follow that with a new command, show IP OSPF neighbors. This will give us a list of neighbors from the perspective of OSPF running on router 3. And we can contrast these 2 reports because we can see here on the CDP neighbors report that neighbors are recognized via their host name, R1, R2, and R4. We can see the local interface being used by R3 to connect to these neighbors. And we can see the capability of these neighbors. We can see what they are. According to this code, we have the letter R. And according to the capability codes table right here, we can see that R indicates router. So we have 3 routers as neighbors to R3. And we can see what kind of interface on each of those neighbors is being used to connect to R3's interfaces. Now, when we compare this to the show IP OSPF neighbors report, we see something a little bit less vanilla, because here the neighbors are specifically named as neighbors, and so we are looking for a neighbor ID, and this would be the router ID that is assigned to each device. We can see router 1, which is 1.1.1.1. We can see router 4, which is 4.4.4.4. But what is interesting here, and why I wanted to use router 3 as the next example in this lesson, is because when we look at the neighbor ID here, this is clearly router 2, because we see the .2 here, and we can see that what router 2 did, because we did not assign a router ID to router 2, if you recall, what router 2 did was it chose its own ID, and it chose the highest IP address it had, which is 10,002. And this makes sense because router 2 is directly connected to the 7,000 network, the 9,000 network, and the 10,000 network. And so obviously 10,000 is greater than either 7,000 or 9,000. So it shows this as its ID. And so I find that very interesting. Now we can also see that OSPF neighbors are further defined by their state. And so full simply means that they are in a full neighbor state. And so that's good. That means everything is working perfectly good. We also see these initials. We see DR, that stands for designated router, and we see BDR, that stands for backup designated router. So a designated router is kind of like the hub or the sort of boss of all the routers in OSPF. And so from R3's perspective, R2 is the designated router. So when all the routers are sharing updates in OSPF, R2 is the router that will give out the updated information to R3. So R3 recognizes R2 as the source for new information for updates. Now if R2 goes down or has some problem, or R3 can't reach R2 for some reason, R1 is the backup designated router, and so R3 will start getting its OSPF information from router 1. Now let's go over here to address. We can see the IP addresses of the OSPF neighbors. So these are the actual interfaces, the actual interface addresses of the interfaces connected to R3's interfaces. And here we see interface, and these are the interfaces on R3 that are directly connected to the interfaces on the OSPF neighbors that are shown here by their IPv4 address. And we can further verify this if we just highlight one. Let's highlight the serial interface. We can see it's serial 010. If we go over here to the vanilla neighbor table, we can see the local interface on R3, serial 010. So that all looks good. Now let's log into router 2. And here the first command I'm going to enter is show IP OSPF with a question mark so we can see the other options we have available to us. We already used the neighbor command, so this time I'm going to use the database command so we can see the link state database. And this just underscores again how OSPF knows the entire topology of its environment. This is unlike EIGRP where routers only know what they're directly connected to. And we can see this is so because on this link state database we can see each of the router's IDs, all 5 routers. Now the other interesting thing here is here under netlink states we could see which routers are advertising to which networks. And this is interesting because you will notice here there's no 7,000 or 11,000 network mentioned. And the reason is because they are serial links. And so OSPF is trying to not use them for link state advertisements or other kinds of updates. It's trying to only use the gig links. So we can see here that router 2 is advertising to both the 9,000 and 10,000 networks. Router 3 is advertising to the 8,000 network, which is connected to router 1. And router 5 is advertising on the 12,000 network, which is connected to router 4. And we know that router 4 is connected to both the 10,000 and 11,000 networks. And again, we don't see 11,000 here, and we don't see 7,000 here. So now we're going to issue a new command, and that's going to be show IP OSPF interface. And this is going to relate to this database, and I'm going to show you how that is. Now let me scroll all the way down so we show the entire report. So remember I mentioned that we don't see 7,000 here and we don't see 11,000 here. This is more pertinent for the 7,000 network, and I'm going to start right here to show you why. So we're on R2. We can see R2's serial port, which is 010. We can see the IP address, which is 7002, and we know that's directly connected to router 1 on 7001. And we can actually verify that if we look down here. We can see adjacent with neighbor 1.1.1.1, of course, that is router 1. Now we can see that the router ID here on router 2 and the process ID, so those are all correct. We can see the cost is 64. We know that's the base cost calculated by OSPF on a serial link. That's correct. But here's the interesting thing, and this is the reason why we don't see the 7000 network on the link state database. Because there's no designated router on this network, and there's no backup designated router on this network. So in other words, let me just close this for a second. So there's no backup or designated router sending information on this network. And the reason is because it's just too slow for OSPF. From OSPF's point of view, it wants to use the gig interfaces and nothing else because they're much faster. So if we go up here and we start at the top, we can see gig 000. This is for the 9000 network. Again, we're on router 2 and we can see that confirmation right here. Process ID 2, router ID 10002, which it chose for itself. We can see the designated router on the 9000 network is router 2. We can see the interface address 9002. So that's the IP address on the interface on the 9000 network on router 2. And we can see the backup designated router, or BDR, is router 3. So on the 9000 network, router 3 is the backup designated router. And we can see further confirmation of that because we can see down here we have a neighbor adjacency with router 3, and it is in fact the BDR. Now the most important thing I would think would be this right here. Now all this is important, of course, but the hello and dead timers. These are one of 3 requirements that must match in an OSPF environment for routers to form relationships. So the hello and dead timers on each interface participating in OSPF on each router in an OSPF environment have to be set at exactly the same. Hellos have to go out every 10 seconds, and then the router has to wait 40 seconds to get a reply, otherwise it will assume that its neighbor is dead or not functioning or whatever. So just make sure that if you get a live simulation during an exam, a troubleshooting scenario of some kind, and you have OSPF routers that are not forming relationships, remember this command. Show IP OSPF interface, and then check the hello and dead timers, because this is one of only 3 things that have to match. So if we go down here to gigabit 001, again we can see this is the 10,000 network. There's the IP address. Again, we know we're on router 2 because we can see process ID 2, router ID 2. We see a cost of 1, makes sense because it's a gigabit interface. We can see the state is DR, so we can see again that the router 2 is the designated router for the 10,000 network. And then on the 10,000 network, the BDR is router 4, and there's router 4's address, and again we get further confirmation. We just go down here and highlight this, and we can see that router 4 has formed a neighbor adjacency with router 2, and it is the BDR. So all of that looks good. And now let's log in to router 4 and run the same command so we can see the difference. Remember, we didn't see a 7,000 or an 11,000 on that database. So let's confirm the same thing on router 4, and then we'll finish with router 5. So I will once again issue the show IP OSPF database command. And again, this underscores how routers in OSPF know the entire topology of their environment, because we can see each router ID represented here. So router 4 knows about all the routers in this environment. And we can also see router 4's view of the network. You can see that router 3 is advertising to the 8000 network. Router 2 is advertising to both the 9000 and 10,000 networks, and the router 5 is handling the advertisements to the 12,000 network. And once again, we do not see the 7,000 or 11,000 networks represented here. So let's do a show IP OSPF interface command. Once again, I will scroll down to show the whole thing, and I will start with the serial interface on router 4, and we can see that is connected to the 11,000 network. We can see the cost, which is 64. That is the base cost calculated by OSPF for routing over a serial link. And notice here we have no designated router on this network and no backup designated router on this network. However, we do have a neighbor adjacency with router 3, and we know that router 3 is attached to the 11,000 network, but OSPF is trying to not use this link. We look at gigabit 000, see the 10,000 network. We can see that router 4 is the backup designated router on the 10,000 network, and that the designated router is, of course, router 2. We can see its information there. We can see the cost of 1, which is the calculated cost via OSPF on a gig link. So obviously 1 is much lower and better than 64. And we can see, of course, hello and dead timers are the same. And we can see that yes, router 4 has an adjacency with router 2, and that router 2 is the designated router on this network. And here we get some more interesting information. We can see that the state of router 4 on the 12,000 network is BDR. It's the backup designated router. Why is that? Because the designated router on the 12,000 network is router 5, which is confirmed here. We can see that router 5 is advertising to the 12,000 network, and we can see router 5's interface address right here, and we can see that on the 12,000 network, router 4 is the BDR. And if we go down here, we can see that yes, router 4 has a neighbor relationship with router 5, and router 5 once again is verified as being the designated router. And so all of that looks good. And finally, when we log in to router 5 and we run some of these show commands, I think you will find this fairly interesting, because these reports are going to be much smaller on router 5 because it's only connected to one network, the 12,000 network. So let's begin with the show IP OSPF neighbors command, and let's contrast and compare that to the show CDP neighbors command. And we can see we have one neighbor in OSPF and we have one CDP neighbor, R4. And so the neighbor in OSPF is R4. We can see that the state is full, so we have a full OSPF neighbor adjacency relationship with router 5. We can see that router 4 is the BDR on the 12,000 network. We can see that R4 is our CDP neighbor, that router 5's gig 000 is connected to router 4's gig 001, and that router 4 has a capability of R for router. So that's pretty good. Now let's do a show IP OSPF database command. And again, this underscores how in OSPF routers know the entire topology, because here we can see that router 5 knows about all the other routers. And we can see that router 5 knows the advertising routers itself, advertising to the 12,000 network, router 3 advertising to the 8,000 network, and router 2 advertising to both the 9,000 and 10,000 networks. And once again, we do not see networks 7,000 and 11,000 represented because they are serial links, and OSPF is trying to not use those for any OSPF activity. And if we look at OSPF interfaces, we get only one interface because router 5 is only connected to the 12,000 network, so we don't have to scroll down or anything. And we can see that gigabit 000 on the 12,000 network. We can see router 5's ID and process ID. We can see the cost of routing on this network is 1 because it's a gig network. We can see that the state of R5 is designated router, and that's further verified here. We can see the designated router ID of 5.5.5.5 and the interface address again, which is on router 5. We can see the backup designated router is router 4, and we can see our adjacency with router 4, and again verification that it is in fact the BDR on the 12,000 network. So let's do a show IP route command. This is the vanilla routing table for router 5. And we can see that now router 5 has learned all of these new routes to these networks, and we can see that it learned them via OSPF because the letter O is the code for OSPF. We can see that when router 5 routes anything from the 12,000 network to the 7,000 network, that it has an OSPF calculated cost of 66. And we can see that all the routing from the 12,000 network must go through router 4 because that is the only neighbor that router 5 has, and it's the only network that router 5 is connected to. And of course we can see the costs for the other networks. So when we route to these other networks, we have these different costs, and we can actually verify those because if we look, for example, 7,000 network, routing to the 7,000 network from the 12,000 network has a cost of 66. And we can verify that simply by counting and looking at the interfaces on each of these links. So we know we have a cost of 1, cost of 1, cost of 64, add those together, and we get a cost of 66. So that all looks good. And I think that's pretty much all we need to do for commands on our various routers. Now let's try to ping the routers on other networks. Before, if you recall, we could not do that. But if everything is configured correctly, and it looks like it is because we have routes to these different networks now that we didn't have before, we should be able to ping across these networks. So how about we ping to the farthest network according to OSPF because it has the highest cost. Let's ping router 1 on the 7,000 network. And so this might take a few seconds, and there it is. So it just took a little bit because it costs a bit more. How about we try pinging router 1 on the 8,000 network? And that went right away, and it probably helped that it only has a cost of 4 to get there, so that's a much shorter path than to the 7,000 network, isn't it? Let's log back into router 1 because I want to show you something that's pretty interesting. And it's another way to verify connectivity and see how OSPF calculates the shortest path, or opens the shortest path, as it were. So if we do a trace route back to router 5 from router 1, we can see that we're passing through router 3. And if we do a trace route to router 2 on the 10,000 network, we go through router 3. And if we do, well, if we go to the 11,000 network, we're going to go on to the 11,000 network. But we can do that. We're going to go through router 3. And let's see, what else can we do? We can go to, how about the 9,000 network? And again, we're going through router 3. And the only time we don't do that is when we use the directly connected network to go to router 2, and we just go right over the 7,000 network. So why are we using router 3 all the time? Well, let's take a look. Show IP OSPF interface. Let me maximize the screen here so it's a little bit easier to see. And scroll down a bit. So we know that router 1 has two directly connected networks, the 8,000 network and the 7,000 network. So the reason why we're using router 3 to route to all those other networks is because on the 8,000 network from router 1, router 3 is the designated router, and router 1 is the BDR, or backup designated router. And again, this is on the 8,000 network, which is the gigabit link. We can see the cost here is 1. And we can see here that we have an adjacency with router 3, and that it is the designated router. So router 3 is designated from the viewpoint of router 1 on the 8,000 network. But on the 9,000 network, router 3 is the backup to router 2. And if we scroll down, we can see some interesting information here as well. So here is the serial link. We can see the cost, 64. We can see it's the 7,000 network. And here, what is very interesting is we have no designated router on this network and no backup designated router on this network, even though we are directly adjacent and have a neighbor relationship with router 2. And again, that's because OSPF has determined that this route over the serial link is so much slower than the gig links that it is better to take an indirect path to go to these other networks than to simply go across here. And that reminds me, in the final lesson of this course, we're going to be reviewing everything we've learned. And during that lesson, I'm going to show you a simple formula you can use so that whenever you look at an OSPF topology, you will immediately be able to figure out which is the shortest path between networks. But for now, I think we're finished with this lesson. And in the next lesson, we're going to simulate a down network so we can see how OSPF recalculates to open the shortest path between the remaining networks. In this lesson, we're going to simulate a downed network so we can see how OSPF compensates for losing one of these links. Now, we could take down the 7,000 network or the 11,000 network, but that really wouldn't make much of a difference because OSPF already prefers to use these gigabit networks because they are much faster routes to all of the networks in our overall topology. So I'm thinking what we should do is take down either the 9,000 network or one of these two, the 8,000 or the 10,000 networks, and then see what OSPF does. Now, of course, before we do this, we want to save our configuration. And that way, we can experiment with our topology and reload it later if we want to try again. So what I think I'm going to do is I'm going to click on the little delete button over here, and if I take out either the 10,000 or 8,000 network, well, let's take this one at a time. If I remove the 8,000 network, router 1 will be forced to use the 7,000 network to route packets to the other networks. And of course, they will all have to redirect traffic over the 7,000 link to router 1. So that's not really going to change very much because they are still going to try to use these gig links whenever possible to route traffic to the other routers. So I think what I'm going to do instead is remove the 9,000 network. And so now there's not an easy way to cross our topology to find a lower cost route for our routers to route packets. So now let's see what happens when we go in here and do a show IP route. And we can see now that the 9,000 network is no longer there. So OSPF has converged fully and sent that LSA. So that's good. So let's see if we can ping. Oh, I don't know. Let's see about, how about the 11,000 network router 4? And yes, we can. Can we ping router 3? Let's see. Router 3 would be 8,003. Yes, we can. And of course, I expect we can ping router 2 over our serial link. Yes, we can. Now, let's try to trace route to router 4. And so we've gone over the 8,000 network, then to the 11,000 network through router 3. And let's try that again. And so that seems very stable. It seems to be working. So we can trace a route from here over to here. So there's no problem with that. So let's try, how about 12,004? So this would be router 4 on the 12,000 network. And we seem to be having some problem. So it seems we made it to router 3, but then the packet was dropped. Let's try that again, see what happens. Okay, that seems a little odd because there is no 9,000 network, so how are we traveling across the 10,000 network? Let's try that again. And that seems a little weird. Let's try to trace a route to the 12,000 network to router 5. And there's a little bit of delay there. And we were not able to get there. Okay, now we are. But I've noticed a little bit of a problem here. We are going across the 7,000 network. And then we are ending up somehow on the 11,000 network. And then we have our packet arriving at router 5. Let's do that again. And now we're getting 8,000, 10,000, 12,000, 7, 11, 12, 8, 10, 12 over and over. So what's happening here is that these are equal cost paths because they each have one serial link and 1 gigabit link. So what's happening is that OSPF is getting a little bit confused. The packets are sort of being load balanced in a kind of clumsy way to get over here to the 12,000 network. And if we go into, let's go to show IP route and look at the vanilla routing table. And we get our verification that is correct because we can see that our route to the 12,000 network has exactly the same cost. So OSPF is having a little bit of a problem helping router 1 route packets across the network to the 12,000 network. And of course we don't like things to be clumsy as engineers because we like things to be nice and neat. So let's see what's happening over here from router 5's perspective. Can we ping router 1? Let's find out. And we can. Can we ping router 2 on the same network? Yes, we can. Let's see, can we ping router 3 on the 8,000 network? And yes, we can. Now let's try to trace route to router 1 and see what happens. And we're going at 12 to 10 to 1, and that is correct. Let's do that again and again just to make sure everything is stable and working correctly. And yes, it is. And so we can see that when router 5 routes traffic to router 1 on the 7,000 network, traffic goes to router 4, across the 10,000 network to router 2, and then on to the 7,000 network. So all of that is working fine from router 5's perspective. Router 5 has no problems. Let's see what happens with router 4. We'll do a trace route to, let's do router 1, but on the 8,000 network, and see how router 4 sends traffic. So it goes across the serial link on the 11,000 network and then across the 8,000 network. So that all looks good. And I suspect the same thing will happen for router 2 and router 3. So the only real problem here is over here on router 1. Because from router 1's perspective through OSPF, there are 2 shortest paths to these 3 networks. And of course you can't have 2 shortest of anything, you can only have 1 shortest of something. So what OSPF is doing in its own sort of clumsy way is it's actually trying to balance the load of that network traffic by splitting those packets over 2 different routes. And of course we don't like to do anything clumsily as engineers. We want things to be neat and tidy and certain. So what we need to do is we have to force OSPF to choose one shortest path across our network topology, and to do that we need to modify the configurations on router 1. And this is actually a good scenario to run through because it teaches us a valuable lesson in troubleshooting. Because in a real production environment like a company network or a data center, you're going to be making small adjustments to configurations to always maintain and improve efficiency. So this is going to be very useful to you, not only for your exams but also in your career. So let's make an adjustment to router 1, and I think the adjustment we want to make is we want to force OSPF to use the 8,000 network as the preferred path to the other networks. So router 1 will still be able to communicate with hosts on the 7,000 network, and it can still communicate just fine with router 2, but when using the shortest path we want it to choose the 8,000 network as the first link in that path. And so to do that, what I'm going to do is I'm going to make an adjustment to the serial interface on the 7,000 network. So I believe that was interface serial 0/1/1, I think it was. And if we type in our question mark, we get a set of options here, and I think the one I'm going to use is bandwidth. So I'm going to adjust the bandwidth on this interface, and we adjust it in kilobits, so I will choose 1024 kilobits. That will set the bandwidth on this interface to 1 megabit, and that is slower than a gigabit. So now OSPF will take this setting into consideration when it calculates its shortest path. So let's exit, and see if that worked. I will save the configuration, and now let's do a show IP route command and look at the vanilla routing table on router 1. And it looks like we have corrected that problem, because now instead of having 2 preferred paths to the 12,000 network, we only have this one, and it's going via router 3. So that all looks good, but let's do another show command just to verify a little bit further. And I'm going to use the show command show IP OSPF neighbors. And we can see here that yes, we have a full neighbor relationship with router 3. Router 3 is our designated router, so that's good. We can see its address here, 8000 network. We see the ID for router 2. Remember, this is also the IP address on the 10,000 network, but right now this is being used as the neighbor ID from the viewpoint of OSPF. And we can see we have a full neighbor adjacency in OSPF with router 2, and correctly we see neither a DR or BDR listed here as the state for this link, which is the serial link. So all of that fits and looks correct. Now let's try to trace route to router 5 on the 12,000 network. And let's do this a couple of more times just to make sure that yes, OSPF has calculated the shortest path, and it is through our designated router on the 8000 network, which is router 3, and there it is. And let's do another trace route, because we can even go a little bit further to verify everything, although it does look good right now. It looks like we have resolved this issue. And that also looks good. So I will close this window here, and I think we can say that we have done some good work and we have resolved this issue. And of course, if you'd like to, continue to experiment with our network topology by removing links or adding links or changing the settings on some of the interfaces, and then observe how OSPF compensates for those changes. In this lesson, we're going to review everything we've learned in this course, along with focusing in on a few key topics that will be important to your CCNA exam. The first thing I'd like to show you is the open shortest path formula. Now, this basic formula is a very abbreviated version of the algorithm that OSPF uses, but it still works well in helping you identify the shortest path in any OSPF topology. And in certain cases, this formula can even help you identify the DR and BDRs. So how this formula works is that whenever you want to identify the cost of a certain path, all you have to do is look at the interfaces on the routers on each of those given networks and then apply the appropriate cost. So for example, if we are routing traffic from an Ethernet network to a serial network, then the cost would be 10 plus 64 for a total cost of 74 according to OSPF. And the same would be true if we were going from a serial network to a fast Ethernet network. The cost would be 64 plus 1 for a total cost of 65 according to OSPF. But there are two additional things you need to remember when using this formula. Number one, remember to include the destination network in the final cost and pay close attention to the last interface that the packet passes through. And number two, a link is only as fast as its slowest interface. So if a packet of data has to traverse a link that has a gig port on one end and an Ethernet port on the other end, then the cost of routing over that network to another network is going to be 10 and not 1. Now let's look at the requirements for routers to form neighbor adjacencies in OSPF. So for routers to be neighbors in an OSPF area, they all have to have the same area ID. And the first area that we must create in any OSPF environment is area 0. The second requirement is that routers must be in the same subnet. And what this means is routers that are directly connected to each other. And when we say subnet, what we really mean is on the same network. That is to say, having the same network boundaries. The third requirement is that the hello and dead timers on each router must be the same. By default, a router will send out one hello message every 10 seconds to its neighbors, and then it will wait 40 seconds for a reply. If the router gets no replies within that 40-second time frame, it will determine that the neighbor router is dead, and OSPF will recalculate a new shortest path. The fourth requirement, if used, is that authentication must be the same on each router. So in other words, username and password for login must be the same on each router if authentication is being used. The next item is the stub flag. In multi-area OSPF topologies, we can create stub areas, but we have to have a stub flag configured to let OSPF know that it is a stub area and not just a normal area. So for example, when we look at our original lab, we could configure the 12,000 network as a stub area, because what a stub area is a dead-end LAN or a cul-de-sac. So there's only one way in or out. Now in our lab, that's router 4. And it bears mentioning that a stub network and a stub area are two different things. They're not the same, because a stub network is just a network. So at the beginning of this course, we could have configured the 12,000 network in one of three ways. We could have made it part of area 0, which is what we did. We could have added an area to our topology and made this area 1, and that would have made our topology into a multi-area OSPF topology. Or we could have further defined it, making it area 1, and then adding the stub flag command with a number that matched the area number and turn this into a stub area. So at this point you might be wondering, why do we even need stub areas? Well, stub areas improve efficiency within an OSPF topology. So let's pretend, for example, there is some internet over here, and that router 1 is our gateway to the internet. This would make router 1 the ASBR, the Autonomous System Border Router. So every time this router learns about a new network out here on the internet, what's it going to do? Well, since it's part of an OSPF topology, it's going to advertise that route to all of the other routers within the topology. But there's no reason for R5 to have a routing table with all of these routes and all the routes from out here on the internet. And that's because router 4 would already know how to get out to the internet. So there's no reason to be sending all those LSAs all over the topology when we could just create a stub area over here and reduce the amount of network traffic. And finally, for routers to form neighbor adjacencies in OSPF, each router needs a unique RID, a router ID. And routers get their IDs in one of three ways. The first is if we manually assign an ID to a router, then that's the ID the router will use. But if we haven't done that, the router will search for a loopback address and choose the highest loopback address it has. But if it doesn't have a loopback address, then it will simply use the highest non-loopback address it has, usually an IPv4 address on one of its interfaces. Now let's learn about the different types of LSAs. LSA stands for Link State Advertisement, and this is how routers in an OSPF environment share routing information with each other. Now in our lab, we had one OSPF area, Area 0. And so when we issued the Show IP OSPF database command, we only saw two types of LSAs, Type 1 and Type 2. Type 1 LSAs show us all the RIDs of all the neighbors and the number of links each one has, while Type 2 LSAs show us which routers are advertising to which network links. Type 3 LSAs are summary LSAs, but they don't summarize a network address the way the auto summary command does. Instead, a Type 3 LSA summarizes the topology of its area for use by another connected area. Type 4 LSAs are only used when a border router has been configured for router redistribution. This is when a border router in an OSPF environment is also connected to another topology that's using a different routing protocol than OSPF. Redistribution allows a router to act as an interpreter between the two different routing protocols and allows them to share topology and routing information between each other. And finally, there are Type 5 LSAs. These LSAs are used to advertise routes to networks outside of an OSPF area. And now a pop quiz. Looking at this network diagram and using only the information that you see, which path will OSPF use as the shortest path from R1 to the 10.10.10.0 network? The answer is on the next slide. Were you able to calculate the correct path? If not, don't worry, just remember these two tips. A link is only as fast as its slowest interface, and the destination network must always be included in the final cost. And with that, you have finished this course. I hope you enjoyed it, and I hope you will continue to experiment with this lab, creating new OSPF areas and maybe even a stub area or two, and then using your show commands to see what new LSAs the routers are generating and advertising to each other. So congratulations for finishing this course, and as always, I hope you enjoy these videos, and I thank you for watching.